Let's start with the friction. Global AI investments are stalling. Enterprise-wide deployments consistently get bogged down by internal data silos and defensive IT posturing. The deciding factor isn't usually the model itself. The projects that succeed secure clear data access and define strict parameters early. The ones that fail hit internal resistance. Pushing past this resistance doesn't mean buying a larger language model. It requires a different architectural approach to how artificial intelligence interacts with your systems. Standard generative AI is largely passive. It takes human intent and translates it into a text response or an image. You prompt it, and it provides an answer. This graphic maps the evolution of enterprise data strategy. The top two tiers show the crucial operational jump. We are moving past generative AI into AI agents, systems designed to actively plan, reason over specific goals, and execute transactions autonomously. Moving into production requires leaving the simple chat interface behind and building a structurally sound, autonomous agentic architecture. You cannot simply plug an agent into an enterprise and expect it to work. Deploying an effective army of AI agents requires building a highly specific, layered technical stack from the ground up. We have to construct three distinct layers: a unified data ledger, a semantic mapping layer to provide context, and an overarching orchestration layer where the agents actually operate. And because we are dealing with global supply chains, this digital architecture has to directly map to physical realities: moving trucks, intermodal trains, and shipping notes. Grasping this exact anatomical structure is how enterprise leaders bypass defensive IT roadblocks and achieve autonomous execution. A large language model operates solely as a reasoning engine. On its own, it is not an agent. This diagram breaks down what an AI agent needs to function. Surrounding the core are four requirements. At the top, goal and instructions provide behavioral guardrails and strict rules. At the bottom, knowledge and tools connect the reasoning engine to real-world enterprise systems. This schematic illustrates how these components synthesize within the agent runtime environment, the orchestration layer. Operating in a continuous loop, an end user submits a query. The runtime breaks it down, uses tools to fetch external API data, processes it, and triggers a specific response. But a perfectly constructed agent remains inert unless it can understand the environment it operates in. It has to be fed by a unified, perfectly mapped foundation of enterprise data. If your enterprise data is scattered across siloed systems like SAP, Oracle, or Snowflake, the agents will fail. They cannot reconcile those fragments on their own. The architecture starts with a foundational, unified master ledger. This ingests and cleanses disparate ERP data streams into a single, governed environment. However, pooling raw data isn't enough. Without contextual definitions, a list of inventory numbers and supplier names is just noise to an AI. Now, this requires a semantic translation layer. We have to construct an ontology, which acts as a digital twin for the enterprise. This semantic layer maps relationships between real-world nodes. It explicitly connects a supplier to a product and traces that product to an inventory location. Defining these relationships allows the system to trace causality, instantly identifying which downstream inventories are impacted by a supplier disruption. Finally, we cap the stack with a decision layer, where specialized autonomous AI agents are deployed directly on top of the semantic map. When a demand agent resolves an issue, it queries the digital twin, utilizing its specialized models and the unified data ledger simultaneously. This complete three-tiered architecture is the strict prerequisite for enabling true autonomous planning across a supply chain. Let's apply this architecture to a significant logistics crisis. Imagine a sudden rail strike that threatens to indefinitely delay inbound freight shipments. This demonstrates a specialized logistics control tower. By monitoring the semantic layer, an autonomous agent detects the potential delay risk in real time. It immediately enters a reasoning cycle, queries the impacted inventory, assesses alternate transit, and autonomously executes a trucking contract to reroute goods. The exact same architecture applies to data-heavy compliance tasks, like cross-border customs or shipment damage detection. This interface shows Google Agent Space managing customs compliance. The agent ingests unstructured data, like PDF packing lists and Excel invoices, and parses the critical details. It cross-references the documents, flags missing a curation, and generates the exact electronic formats required for filing without human translation. By structuring the underlying data correctly, what used to require days of manual crisis management and data entry is condensed into seconds of autonomous execution. At this point, the primary barrier to implementing an autonomous supply chain is no longer technical capability. As this slide from the AI for High-Tech event highlights, the biggest hurdle is organizational change and cultural inertia. Enterprise IT departments are justifiably defensive. They reject opaque, open-ended science experiments. They demand predictable business outcomes. The strategic antidote to this internal friction is a deployment model known as the progressive glassbox methodology. It is designed to offer fixed price, fixed cost, and fixed code guarantees, delivering functional agents within rigid 4-week sprint cycles. Instead of a legacy black box software deployment, the glassbox approach makes the entire process transparent. It exposes the exact data lineage and semantic relationships, proving to IT leadership exactly how the AI arrives at its decisions and generates value. By combining a rigorous semantic agent architecture with a highly transparent deployment methodology, enterprises can stop debating the potential of AI and start realizing widespread operational autonomy.